Everyone, thank you so much for coming to Popping the Science Bubble. Tonight we are at the West Branch Public Library, so Science Bubble is still on the road. I'm going to go ahead and read our land acknowledgement, and then I will introduce the Science Bubble program. Berkeley Public Library buildings are built on the territory of the Huichin within the homeland of Chochenyo-speaking Ohlone people. We acknowledge and honor the Ohlone people who have lived in Berkeley and throughout the East Bay since time immemorial. The library recognizes that Berkeley residents have and continue to benefit from the use and occupation of unseceded stolen land, and we pledge to recognize the permanence and the rich contributions that the Ohlone people continue to bring to the city of Berkeley and throughout the East Bay. We celebrate the strength of the Ohlone people and their culture. The Berkeley Public Library is committed to helping create a more just and anti-racist society and to furthering the visibility and celebration of Ohlone authors who are specific to the East Bay and Ohlone culture in our collections and programming. This is a living document that was co-written by Ohlone cultural leaders, Vincent Medina and Louis Trevino, and the Berkeley Public Library. All right, so welcome to Popping the Science Bubble. This is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. We have two speakers at each seminar who will talk about their current research or a topic that they find really interesting. The organizers are two graduate students at UC Berkeley, Helen Schwang and Daniel Brethauer. This program happens every third Tuesday of the month at 5:30 p.m. at the library and on Zoom. If you're interested in checking out their past seminars, you can visit their website and sign up for the listserv to keep in the loop for upcoming seminars. Also check out their YouTube page to view this lecture and see an archive of past lectures. And the past lectures are just really amazing. I do recommend going to see what they have. All right, so I'll let Kaylin introduce tonight's speaker.
All right, thank you so much, Kelsey, and welcome all, and hi everyone on Zoom. And like Kelsey mentioned, we will have a QR code at the end where you can scan to sign up to join the listserv. We will have some resources that our speakers share with us. If you want to check out more about what they talk about in their talks. And for tonight, we are excited to have Davidek and Tai Xiang with us to present. This is an open format talk, so you can raise your hand for questions, and for folks on Zoom, feel free to use the Q&A section and we'll ask the question. And so to start us off, tonight's first speaker is Davidek. Ivan was born in Michigan, but moved to California when he was in middle school. He took classes at Monterey Peninsula College for 3 years before transferring to UC Davis in 2020. After graduating with a BS in biochemistry and molecular biology in 2022, Ivan worked for 2 years in Professor Nathaniel Gray's lab at Stanford University. Since 2024, he is a PhD student in the College of Chemistry here at UC Berkeley, working in Professor Robert Saxton's lab. Outside of research, Ivan likes to go to the gym, cook, and backpack, and also enjoys listening to live music and full sleep.
Awesome. Thank you, Caitlin, for the intro. Yeah, so today I'm going to be talking about how we can use the immune system to defeat cancer. And so I've titled the talk Ready, Set, Go, pressing the gas pedal of the immune system to defeat cancer. So I'm going to tell you a little bit about some cancer biology and then previous research that has been done at UC Berkeley, actually, and then a little bit about my research, which is kind of just starting in this field. So cancer, as many of us know, is a disease of uncontrolled cell growth. And so here is an image of 2 breast cancer cells dividing. But what most people don't know is actually what causes cancer. And so there are some direct genetic causes that are passed down through families, but actually most of the time, it's an accumulation of mutations in lots of genes that are happening over the course of a lifetime. And the genes that are going to be mutated in cancer are two separate classes of genes. You're going to have tumor suppressor genes, which will get mutated. So these are genes that we have that their sole purpose is to prevent the formation of cancers. So when these get mutated, that alone is not enough to cause cancer. But then you also have another class of genes called proto-oncogenes, proto meaning giving rise to, onco meaning tumor. So it's a gene that can give rise to a tumor. And so when these get mutated, they also have the capability of causing cancer. If you just have mutations in one or the other, it's not enough to cause cancer. You need to have mutations in both. So both tumor suppressors getting turned off and proto-oncogenes getting turned on through mutations. And so this relates to the central dogma of molecular biology, basically just saying that you have a gene, which is in the form of DNA, and this creates RNA, which creates a protein, and then this leads to some phenotype. So in the context of cancer, the protein will be mutated, and so you'll have a cancerous phenotype. So this is one of the reasons why we aren't getting tumors all the time, is because you actually need to accumulate a lot of mutations across many genes. But then also your immune system is constantly surveilling your body for cancerous cells, and is destroying them before they turn into a tumor. So I'm going to focus on the immune system part of how the immune system deals with cancer, but the immune system does need to deal with a lot of possible infiltrations into the body, worms, protozoa, fungi, bacteria, viruses, and also cancer. So there's a lot of different types of pathogens or foreign invaders in the body that the immune system is. And so since it has to deal with a whole variety of different pathogens, there's a huge variety of immune cell types that exist that can deal with all sorts of different pathogens. So you can see in this image, it's basically just a lineage of all the immune cell types, and all of this comes from the far left, which is bone marrow cells. So I'm going to be focusing in a little bit more on one part of the immune system, which are called T cells. They're part of the adaptive immune system. So what does this mean? So T cells in the body can essentially detect and kill almost any foreign pathogen. So they are not specific for one or another type of pathogen. They're very broadly applicable. And the reason we call them adaptive is because once they encounter a pathogen once, the next time you encounter that same pathogen, the immune response is going to be a lot stronger. So this is actually the basis of vaccination. When, let's say, you get vaccinated with a COVID-19 vaccine, spike protein will go into your arm, your body will see that, and you'll have a T cell response. And the next time you see that spike protein, you're going to have a much bigger response. So they're important for responding to pathogens, but for what I'm talking about today, they're really critical for preventing cancer. So just a little bit more background on T cells. I think this cartoon pretty nicely describes how they come to be. So basically they originate in the bone marrow. They progress to the thymus, which is an organ right below your neck. And here they get trained, so to speak, to be reactive to foreign pathogens, but not to self most of the time. So autoimmunity does exist, so this process is not perfect. And there are mechanisms in place in the human body to tame the immune system to prevent autoimmunity. And we're going to actually come back to that in a little bit. But once the T cells leave the thymus, then they can circulate and respond to pathogens and cancer. So how can T cells recognize cancer? So this is a very simplified diagram, but basically shows you everything you need to know. So on the left is a T cell, so your immune cell, and on the right you have a cancer cell. And so remember I told you that the driving force of cancer is the huge mutational burden that comes over time. And so cancer cells will display mutated proteins on the cell surface. And these are going to be recognized by T cells as a foreign protein because they were not trained to recognize this protein as self. And so the T cell will see a foreign protein and think this is not part of the human body, so we must kill this cell. And so the T cell gets activated and then very efficiently and precisely releases molecules that will kill the cancer. Yeah. And importantly, they don't actually kill healthy cells. So this interaction doesn't occur in normal cells, or with normal cells rather. So then you might be wondering, why do we still get cancer? T cells have this way to identify mutations in cancerous cells. How come cancer still exists? And so there's many reasons that they still exist, but one of the reasons is that cancer actually exploits the body's natural defense against autoimmune. So in the previous image that I showed you, I just showed you the T cell receptor recognizing mutated proteins on cancer. But there's actually more going on in this picture. T cells, also on their surface, have an immune checkpoint receptor. So this is basically like a second check for this for the T cell to know, is this a human cell or not a human cell? And if the cancer cell or another cell is displaying an immune checkpoint protein, that can interact with the immune checkpoint receptor and essentially tell the T cell, hey, actually, you don't need to get activated. You can chill out. So even if you have a mutated protein on the cancer, the T cell still will not get activated because it's being silenced by the immune checkpoint protein. And so this is like a normal way to quell autoimmunity because all of your cells are going to be displaying this immune checkpoint, but cancer really utilizes this and expresses a lot of this protein on its cell surface so that your immune system doesn't recognize it. And yeah, so basically the T cell is not quite sure if it's cancer or not, and so it just doesn't really kill the cancer cells. So the next logical question is, what happens if you decide to block that immune checkpoint interaction? And so now in this diagram, I've included an antibody, which is a drug-like molecule, which can very precisely block the interaction between the immune checkpoint receptor and the immune checkpoint protein on cancer. And so in this way, you can block the silencing mechanism and the T cell can get normally activated by the cancer. And so the person who did a lot of the pioneering work on this was Jim Allison, actually at UC Berkeley. So he got a Nobel Prize in 2018 for this discovery. And basically what he showed was that in mice, if you, I'll show this here. This is the only data that's here, I swear. But essentially, in mice, if you inject them with a human tumor, and you either give a drug that blocks the immune checkpoint interaction or just a control, like a saline injection, you can see on the graph on the top right, when you give saline, that's the dark black circles, the tumor increases in volume quite a lot, and at 90 days, all the mice die. Whereas if you give them the drug that blocks that interaction, which is the white squares at the bottom, the tumor completely goes away, and actually all the mice ended up surviving. So this was a huge discovery at the time, but people actually didn't really notice it all that much. At that time in 1996, when this came out, there was many drugs that were put into clinical trials and had failed trying to use the immune system to treat cancer. So actually, when Jim discovered this and tried to bring it to pharmaceutical companies to bring a drug to market, he actually was not able to because there was so much risk involved because of all of the previous failures. Luckily, eventually he did find a small biotech to partner with, and they did bring this drug to market in 2011. And as with many groundbreaking discoveries, once the first one is made, then there's a whole host of others. And so now there are 9 FDA-approved immune checkpoint inhibitor drugs. Question, yes, please.
So do normal cells not display these immune checkpoints?
They do. They do.
How do you discriminate as a cell or as a T cell, how do you discriminate between the immune checkpoints that you should block versus the ones that you should not?
That's a great question. So the question for if Zoom did not hear is that, how do you discriminate between blocking the immune checkpoint on a normal cell versus a cancer cell? And essentially you don't. These drugs, they block it in all cells. And so they do cause a lot of autoimmune side effects when you are taking them, like skin rashes. I think 9 to 10% of patients get colitis, so just like inflammation in the colon. So it basically turns on the immune system, not just against cancer, but everywhere in the body. The reason that it can be effective is because the cancer does have that high level of mutation. And so there's more of a signal from the cancer to give to the T cells to kill the cancer, whereas for normal cells, there's not as much of a signal. So there are 9 approved inhibitors, but actually 7 of them are targeting the exact same one immune checkpoint called PD-1 and PD-L1. But there's a lot of these immune checkpoint molecules that exist. It's not just PD-1 and PD-L1. And you can see if you look into the efficacy of these drugs, they are really efficacious in some scenarios. They can have like insanely good results for a small population of patients. But actually for the majority, they don't really do much. And so there is a need to find new immune checkpoints other than just PD-1 and PD-L1. Because if we can drug these, then maybe there will be more patients that can have a benefit from this. So this is where my research comes in. So basically, oh yes, question, please.
Just maybe you're getting into this, but does any one given cell, it has multiple immune checkpoints, or is it that different cells sort of specialize in the immune checkpoints you have, and so you have to target?
Yeah, that's a good question. So basically, do
when we're searching for new immune checkpoints,
Mhm.
are those ones that are going to be on every cell or just a subset of them?
I mean, I guess ideally you would want to have immune checkpoint proteins that are just expressed on cancer, but they are, as far as I'm aware, they're ubiquitously expressed, or they're like on all cell types.
And different cells will often have like multiple different types of these proteins, like they'll have multiple checkpoints at the same time.
Yep.
Thank you.
Of course. Yeah, so basically for my research, I'm trying to see, are there new immune checkpoints that we can possibly block to stop the silencing of T cells by cancer. So I won't show you any like data or anything that I am making day to day, but I will tell you about the most common experiment that I do. I would say almost weekly I do this experiment, which is a mouse T cell activation assay. So basically, I'm trying to recapitulate this cell diagram in a petri dish with mouse T cells. And so the issue here is that when you're studying two different cell types in one dish, it's actually kind of hard to distinguish between the two. You definitely can, but it's a lot simpler if you're just working with one cell type. And so what you can do is actually just get rid of the other cell and add in your mutated protein and your immune checkpoint protein to the mouse T cell and see what the activation response is. So for each part of this, I'll just describe how I obtain it and what I do with it. So for the mouse T cells, I actually will euthanize a mouse and then basically take its spleen out and just extract just the T cells from the spleen. And then we can use that in this experiment. For the proteins that I'm treating the T cells with, I will make those in a special protein producing cell line. And there are some images of that. So on the left, you have a cell incubator. So it's kept at 37 degrees C and 8% carbon dioxide. So it's like ideal for these cells to grow. And they're constantly shaking and they're basically just making protein for me for 5 days. And then I'll take them out in the middle. And then on the right, I can basically take all of the cells and do some processing to them to get the protein that I'm interested in, and then purify it using fast performance liquid chromatography, which basically just on the right gives me a protein in some liquid in a tube, and then I can use that to treat the T cells. And then lastly, after I mix the T cells with the proteins that I've made, I can assess for activation by using an instrument called a flow cytometer, which basically just assesses the levels of proteins on the cell surface of a cell. So to conclude, I'll just go through the main points of what I discussed. So T cells recognize mutated proteins in cancer cells and eliminate them. Cancer uses the body's natural autoimmunity defense mechanism to protect itself from T cells. If we block the immune checkpoint, then this enables T cells to kill cancer cells. But we need more immune checkpoints to be discovered because current therapeutics have limited efficacy, and my research is involved in trying to find that. So thank you all for listening, and I'll happily take any more questions if there are any.
Very basic question.
Sure.
How does this method contrast with the other means that we have for treating cancer currently? And what are the possible advantages that make it, make you motivated to continue to look for additional checkpoints? Like, why should this be expanded?
That's a great question. Yeah, so basically the question is like, how does this compare to current methods of treatment and why is it important? So up until the 1990s, most of the or I might say like 1970s, 1980s, most of the ways of treating cancer involved just broadly toxic chemicals. And it relied on the fact that cancer cells just divide very quickly. And so if you treat the whole body with very toxic chemicals, then the cells that are dividing the fastest will die while everything else should theoretically survive. As you move on to the end of the 20th century, we developed more targeted therapies. So we came to an understanding that mutations are like broadly what drive cancer. And so there are many drugs that have been developed to specifically target those mutations. But for all of these, we're still just focusing on the cancer itself. And the difference with immune checkpoint inhibition is that we are, instead of focusing on the cancer, we're more so focusing on the body's immune system. So trying to remove any roadblocks that exist for the immune system to kill the cancer. I would say, practically speaking, the benefits are that these drugs can be administered very infrequently. I think the dosing schedule is like once per month or once every 2 weeks. Compared to chemotherapy where you have to come in basically every day and get an infusion. Yeah, I would say, yeah, I think I have no more to add. Yeah. Sure, question, please.
Can I follow up on
Yep.
that? So I'm curious, how long is the course of treatment with the inhibitor? Is it about the same timeline as like chemotherapy?
Chemo, that's a good question. I believe it's similar. But I'm not 100% sure. What's interesting about the immune checkpoint inhibitors is that you actually don't see an effect right away. So that was an issue with the clinical trials that were run initially, because typically you'll run, let's say, a trial, like clinical trials are really, really expensive to run. So how they're typically done for cancer is like maybe a 12 weeks and you're just looking at, is the tumor shrinking? But for these drug, actually, you don't see any effect in that time. You have to wait kind of a while for your immune system to actually start responding to the cancer. So if you're just looking at a small scale course of treatment, there's no effect. But when you look at, like for the clinical trials for these drugs, they mostly look at 5-year survival. And those rates there's a really staggering difference. So I know I'm not exactly answering your question, but I think it's similar. I think it's a similar time period. It's just the duration of or how quickly it takes into effect is definitely different.
And you mentioned that some of the inhibitors are more efficacious for some cancers than other ones.
Yeah.
What are can you give examples?
Sure. For sure. Melanoma and some colon cancers, they are more effective. In general, they're more effective in what we'd call hot tumors, so tumors with a lot of mutations, because in the end, you do need the T cell to still react to the cancer cell. So there are some types of cancer where there's actually not that many mutations, and we still don't really know why the cells are cancerous in that case. But for those tumors, these drugs are not really effective because there's not anything for the T cell to react to, even if you take the brakes off. Sure.
We have 2 questions on Zoom.
Okay.
Roche announced today an oral drug that has been shown to cut the risk of recurrence of a form of breast cancer. Is it likely that these types of drugs are intended to aid the body's immune system? Do you need me to read that again, or?
So the question was, so basically Roche has announced a new breast cancer drug today. And is this drug kind of in the similar class?
Yeah.
I don't know about the drug that Roche announced, but if it's an oral, they said it's an oral drug.
Yeah.
Probably not, because oral, so this, the class of immune checkpoint inhibitor drugs are antibody therapeutics, and basically just means it's a protein drug, and they can only be only delivered through IV, not orally. So I don't think so, but I'm not sure. I haven't heard the specifics of this drug.
Yeah. And if you also want to like respond after, during our break or something too.
Sure.
Janice asks, cancer cells are good at hiding from treatments such as in the peritoneum. Not pronouncing that right. How do these drugs work on that aspect of cancer? Are newer checkpoint drugs designed with that in mind?
Can I see how how they pronounced them?
Yes, under the
Or how they spell
Q&A.
it?
Yeah.
Oh, can I see it?
Yeah, you,
Oh,
I think so, yes.
iris. That's a good question, but I'm honestly not familiar with what peritoneum. Yeah, I'm a bit stumped. I'm not quite sure, but it's a good question. I would assume it's like a certain tissue type or cell type. But yeah, not too sure to be honest.
Oh, good.
Alright. I think we've, and that's the end of our Zoom questions, so, yeah,
Awesome.
alright.
Thank you. Oh, yes.
Just a quick question.
Sure.
So, regarding like this kind of treatment, would the delayed efficacy be one of the main reasons that somebody would choose chemotherapy instead of that? Is the research kind of one of those issues? Do you see this research becoming a lot more effective than chemotherapy, or is it now?
Yeah, it's a good question. So basically, because it takes some time for it to come into effect, is that actually a consideration when we're considering treatment options? I'm not too sure, to be honest, but I will say that typically these drugs are not prescribed alone. A lot of the time you do have combination therapies, and in fact, when you're running clinical trials for cancer, most of the time you're not just comparing like a control to drug, because then everyone in the control group is probably going to die. You're typically comparing like if you have, let's say, a pre-approved, like an already approved drug versus the drug plus a new drug. And so that's how we know a lot of these drugs are effective. So I guess to answer your question, I'm not sure, but probably they're prescribed in tandem most of the time anyway.
And is there like a big risk for like just sickness in general? I mean, 'cause your immune system is just completely down. Is that something that's like slowing down the process of this getting out, or?
Yeah, I mean, as far as I'm aware, like the side effects are definitely there. Like there are a lot of autoimmune like side effects from these drugs. But my impression is that the side effect profile is better than for a lot of chemotherapy drugs. Yeah, it seems like patients tolerate them better.
So when this is like kind of more approved and more broadly spread out, you see this being used much more commonly than chemo or alongside with chemo?
I mean, I would say it is already used quite commonly now for like very specific cancer types. It's used just as much, I would say, because they are approved and they are effective. I think the only consideration is that a lot of the drugs are still not generic, and so they're probably very expensive. So as a patient, they need to consider that as well. But yeah, they're up there with the normal, like I guess you'd call like standard chemotherapy drugs.
Thank you.
No problem. Thank you so much.
So, while we are transitioning, I will be introducing our second speaker, Tai Xiang. Tai moved around between the US and China before sticking around longer in Southern California. He did his undergrad at Pomona College in physics and computer science and currently works on experimental atomic physics in the Stanford Kern Group. Outside of the lab, he is typically rock climbing in the gym or the various cliffs and mountains around the area. So while we're still getting set up, I believe he'll tell us more about quantum computing. Hopefully we get okay.
Oh, I see. I see. Okay, this has been a okay.
We're going to share the
Yes.
screen to.
Yeah.
Awesome.
Perfect, yep, that works.
And then who else I put the Gonna go on there. And go to more. So a couple more to the right. One more. Here we go. And then hide floating points. There's that. That's a lot.
All right. All right, so let's get started then. Yeah, so my name is Ty. I'm from the Stanford Chrome Group of Berkeley. We do sort of a bunch of experiments in studying quantum optics and atomic physics. Although today in particular, I'm just going to comment a little bit about how one actually builds a quantum computer from atoms and cavities, more so on the atom front. I think I have too many slides and we probably won't get the cavity front. And just to kind of give a general overview of like how one actually builds such a device in the lab and what they may be useful for, what are the kind of the big challenges and hurdles and such for the field. And that, as you may be aware, my slide will transition. She doesn't seem to want to. Yes, so quantum, the word in general has become a bit of a buzzword. It kind of gets stuffed in a lot of places. You have like fishing rods called quantum. You have Marvel movies with the word quantum in them. You have flat screen TVs. When I was introduced, I do a lot of climbing, and like I was very shocked to find a climbing shoe company naming one of their models a qubit, which is a quantum bit, which is an interesting name to name a product. And if you want to kind of tell people that it's like not very useful currently and doesn't work that good. But also, there's been a lot of outside financial investment as well, particularly, federally. You hear about this whole kind of quantum competition between, for instance, the US and China. And, recently the California government has also been very invested in this quantum game. So in this case, Gavin Newsom came down to our lab and the sort of new California Quantum Initiative bill was actually signed in Campbell Hall at UC Berkeley, which is where our lab is located. So yeah, there's us hanging out with Gavin. But anyhow, to kind of give a general overview of what I kind of want to tell people about today, first we'll begin with kind of a brief overview of like how classical computing actually works and how we're sort of going to build an analogous system just with some very different building blocks. Then we'll discuss like why does this actually matter? What is the advantage you get? It's sort of like an opaque thing initially, and it kind of comes from this very strange kind of interference phenomena that arises when you begin sort of looking at these very small scaled objects such as atoms. And then I'll discuss how actually you build this sort of quantum computer out of a single atom or many single atoms. And then also kind of discuss the largest hurdle that currently people are trying to overcome, which is this idea of how do you correct errors when it comes to these quantum bits. And then if there's time, I'll talk a little bit about how we use these things called optical cavities to aid in this error correction effort. And finally, kind of talk about what's next and what are the outstanding challenges as people kind of try to push this, pretty fragile system that is beginning to show signs of promise towards a much larger scale and useful kind of system. So just to begin how a classical computer works, we can think of it in this kind of transistor model, where you have a bit of either 1 or 0. In this case, on the left, this sort of wire you can think of as open. So if we put in, say, a voltage or like a current of some sort and it flows, then it will not actually cross the other side. And so this is what we consider a 0. But then, past a certain threshold, this sort of wire is essentially connected and you have a 1. So the idea in this case of a transistor is that, past an explicit voltage threshold, then you have what is, a 1, but voltage below the threshold corresponds to a 0. And that's how we build, these classical devices of 1s and 0s and many, many bits. Arrays and arrays of transistors that either correspond to 1s or 0s, depending on what voltage is applied across them. And then to create gates, what we think about as kind of the basic logical operations and building blocks, we can tile together multiple transistors. So on the left here, this is an OR gate. An OR gate meaning, if I have 2 transistors and I put them together, if both of them are 1s, or if a single one is a 1, then we consider this a 1. But if both of them are 0s, then it becomes a 0. And you can kind of see how this works from the diagram in that there's kind of 2 wires that must be connected, only 1 wire must be connected in order for current to successfully flow across this kind of junction here. And so as long as a single transistor is over the threshold and the wire is connected, then the current has a way to travel. Whereas for the case of an AND gate, where it yields a 1 only if both sort of transistors are ones, you can see that essentially it's sort of in series. So if even a single transistor is a zero in kind of a broken wire, then no current will flow across this junction. And only if both of them are closed and ones can the current kind of flow across the wire and give you a one on the output. And that's kind of the basic ideas of how you construct gates from sort of individual transistors. And from these gates, then you can build up computations. So on the left diagram, I'm not really going to bother to explain it, but the idea here is by combining many of these kind of 2-bit gates or single-bit gates, you can build up things like adders or sort of bitwise multiplication, so on and so forth. And the nice thing that is sort of a part of this kind of classical architecture is that you only need a small subset of gates, such as like an AND gate or an OR gate, and tile them together to essentially realize universal computation, and that you can kind of realize any logical operation that you need to do on a computer to get some sort of result that you desire with a very small subset of gates. You don't need sort of infinitely many gates to do sort of any arbitrary operation. It's a very small subset of gates that you need. So this is kind of the basics I want to talk about when it comes to actual classical computation and how we sort of use transistors to do these kind of mathematical operations or render things on a computer screen. So then moving on to the quantum side of things. So classically, we only have a 1 or a 0. Either the voltage is above the threshold and the current goes across the junction, or sort of you don't have voltage above the threshold and the junction is effectively open and no current can flow through. But when it comes to quantum mechanics, you have this extra possibility. You have what is called sort of a superposition state, essentially, some sort of kind of oddball mixture of both 0 and 1. And sort of the important thing to note about this extra degree of freedom is this little symbol I've drawn here. Now, you don't really have to know what it means, but essentially it's an additional thing called a phase. And this phase is what gives you like an almost analog-like degree of freedom. So whereas in the sort of transistor case, it was all or nothing, either 0 or 1, now you have this additional phase degree of freedom that is enabled just by the intrinsic nature of quantum mechanics. And these sort of quantum mechanical properties occur when you begin to use basic building blocks that go below a very particular length scale. So think something on the size of an atom is when these quantum effects take hold, and sort of objects such as atoms begin to have this thing called phase information. And we want to essentially use this phase degree of information as an almost analog-like sort of property that we can then use to do logical operations that have more power than basic 0 and 1s of transistors. And you may have heard of kind of this old paradigm of like analog computing. So instead of a voltage will correspond to a threshold value, a 0.1 volts will actually be sort of like 0.1 volts, or like 0.8 volts will actually be 0.8 volts. Things will sort of operate on a continuum. You can think of this phase as something very similar to that, although you'll soon find out that the thing that kills analog computing actually sort of does not kill quantum computing for sort of a very interesting reason. But for the time being, you can think of this phase degree of freedom as kind of a additional chunk of information that is almost continuous. And I guess this animation is not rendering very well, but the way we like to think about these things is that in the case of the transistor, this kind of green arrow pointing to the 0 corresponds purely to the 0 state. And then if it points down, then it purely corresponds to a 1 state. But the quantum sort of object has the full continuous degree of freedom to be able to rotate arbitrarily around the sphere and accumulate some phase value. So effectively, you have a whole continuum of sort of numerical phases that can be assigned onto a single bit that then you can use for interesting sort of logical algorithms and different computations that simply is not achievable in a classical setting, and that this phase degree of freedom simply does not exist for these classical devices. So that's kind of the big idea as to why people are interested in quantum computing. Essentially, it's this extra phase degree of freedom. But the end of the day, is sort of an interesting thing, though, is that indeed the system evolves with this phase degree of freedom and possesses this phase degree of freedom. But as you may have heard, measurement actually sort of destroys the phase degree of freedom. And what happens is, say your arrow here is pointed maybe in the sort of 45-degree angle between, or the 90-degree angle, let's say, between the 0 and the 1. So you're halfway between 0 and 1. When you actually make a measurement, you do not preserve the phase information. What happens is, probabilistically, you will collapse this arrow either to the 0 or to the 1. But the location that your sort of arrow is pointing to on the sphere sort of gives a particular probability to whether your state will end up in the 0 or 1. So if I am sort of, for example, perfectly parked in between, sort of on the sphere between 0 and 1, and I say I make 10 measurements of this system, then we'd expect that 5 times out of 10 we will point to 0 and get the result 0, but the other 5 times we'll point to 1 and get the result 1. And so this is kind of this weird concept. The system sort of evolves with this phase, and the phase information is present, but as soon as you measure it and actually want to get the information out, you destroy it. But the sort of various probabilities you get when you measure the system kind of help you kind of recover this information slightly, but it's not sort of an exact one-to-one mapping of some sort of analog system. So this is kind of the confusing part. The other neat power of a phase is the fact that you get this interference phenomena that actually is very classically well described. So you can think of it, as sort of waves, like water waves, for example. And waves have this thing called a phase, and you can kind of look at it in terms of this diagram. So on the sort of top here, when 2 waves are, for example, in phase, you can see that these sort of peaks are well aligned. So they will add up, and you will get sort of a bigger output. But if the waves are out of phase, meaning sort of the peak of one wave is aligned with kind of the valley of another wave, then essentially the amplitudes of these waves will add up and cancel, yielding sort of essentially nothing. And so you can see this in this kind of quantum object as well. I guess these animations don't really work. But you can imagine, for example, if you had many atoms, all with some phase that was evolving, and you set things up so that the phases evolve together, then these amplitudes would add up. If they kind of evolved randomly, then they would kind of all precess in different directions, and the phases would become a garbled mess, and you would get no information. But with this additional interference degree of freedom, you can then imagine putting together many different quantum bits, all with different phases. And by engineering the phase of each bit, then you have sort of access to many, many more sort of powerful algorithms and degrees of freedom that can give you sort of very surprising results. And so some results that people like to talk about, for example, you don't have to, this is just a circuit diagram of this, but you don't have to actually understand what this means. But an example is Shor's algorithm, which tells you that actually by leveraging the quantum phase and using this degree of freedom to your advantage and performing particular operations, you can actually crack RSA encryption, which is kind of the principal means of encryption we use to store data and keep it secure. You can crack RSA encryption with a quantum device in sort of logarithmic time, which in other words is you can do it really quickly, which is why you may have seen governments and whatnot kind of all getting on this quantum train, and that people are afraid cryptography will be broken and whatnot once somebody actually builds a quantum computer. And there's sort of another example of an algorithm is this thing called Grover search, wherein you can quickly search through a whole database of files by once again leveraging this phase degree of freedom. Any other question?
Would you talk a little bit about how do you make sure that all of these qubits are with the same phase, so or I guess perhaps anti-phase, so that you can impose this constructive or destructive?
Okay, yeah, I'll bring that up a little bit later then, when we get to kind of a more experimental part of how we actually construct these things from atoms. So this quantum bit, or as I'll start calling it qubit, how can you actually make one? In this case, I'll talk about it from the perspective of making it out of single neutral atoms. And what we see here actually is a camera image from the lab of actually single rubidium-87 atoms held in a tightly confining laser beam that we can actually sort of take pictures of essentially. So what you're looking at here is actually just a 1D chain of individual atoms, just sort of in free space, a camera image of that. And to prepare such a thing, there's sort of many different steps. You may ask many questions. How do you actually hold a single atom? How do you measure a single atom? How do you prepare the state of a single atom? How do you move them around or sort them? And how do you make these arrays bigger and bigger? And this is all a very sort of kind of complicated technical operation, and the sort of cookbook we're going to follow is we're going to shoot a bunch of rubidium gas first into a vacuum chamber. Now these atoms are going to be really hot and sort of all bouncing around, moving around. So we actually need to cool them down so we can get very good fine control over them. And the means by which we do this is this method called laser cooling, where you can actually use a laser to remove momentum and velocity from these atoms and effectively lower their temperature to sort of microkelvin above absolute zero. And the sort of apparatus by which you do this is this thing called a magneto-optical trap, where you send in 6 laser beams in sort of each of the 3 principal axes, and you have sort of oscillating magnetic fields sort of above them as well to essentially realize a trapping and slowing force. Then we'll project these things called optical tweezers down to capture atoms out of these this kind of very cold, dense ball of ultra cold gas. And then we'll use these things called light-assisted collisions to actually get rid of many atoms that are trapped in these optical tweezers until we get down to single atoms. And then we'll sort of move around our tweezers so that we can realize, you know, a particular array that has no defects, no holes in it. So we can always deterministically prepare an atom array with the exact same amount of quantum bits in them. Yeah. And the way we do this is with a thing called a spatial light modulator or a acousto-optical deflector. The big idea is you can send in one laser beam into this device, and via applying sort of a particular tone of a very particular frequency, you can sort of deflect this laser beam to a very explicit position. And you can see that if you want to sort of move the laser beam, you simply sort of ramp this frequency tone from one point to another, and the laser beam sort of moves along. And then you might ask, well, if I want many of these tweezers, I just send in sort of a combination of many different tones simultaneously. And if I want to move sort of any arbitrary tweezer, I simply move that tone corresponding to that particular tweezer. And so this is why sort of these optical tweezers are very powerful for neutral atom quantum computing, and that you can simply keep sending in tones to make more and more tweezers. And then you'll have sort of these tweezers projected down into your big ball of gas. Yeah, question?
When I hear tweezer, I'm like imagining a bathroom tweezer, which I know is not what you're talking about. So can you kind of give me a sense of like the scale of these tweezers? I guess I'm wondering if you can describe them in a little bit more detail, because it's hard for me to imagine.
Yeah, so we call them tweezers just because you can hold things in them very precisely, but they're actually like a very tiny, tiny laser beam. So you have very small, like sort of wastes. They're on the micron scale. So that's 10 to the minus 6 meters. And they kind of focus down very tightly so that you essentially generate this kind of gradient of light force that always pushes the atom to the sort of tiniest part of the beam. And that's how you kind of trap the atom there. And that as soon as the atom kind of moves away from the center, there's a force that always is trying to confine it to the waist of the tweezer, because that's where sort of the force gradient wants it to go.
Thank you.
But yeah, so you'll project all these tweezers down into your sort of big ball of gas, your sort of magneto-optical trap, which has your ultra-cold gas in them. And each tweezer will capture like a bunch of atoms, right? The tweezer is big enough in that it's a micron scale thing, but atoms are sort of picometer scale, which is 10 to the minus 12, so much smaller. So usually you'll capture many, many atoms in your tweezer, but via this thing called light-assisted collisions, wherein sort of 2 atoms actually collide with one another and have enough energy to form a molecule. And this molecule then has too much energy and the tweezer can no longer hold them. The atoms are ejected in pairs. And so if atoms are continually being ejected in pairs, at the end of these light-assisted collisions, your tweezers either contain a single atom or they contain no atoms. And so after this process occurs, you can take a camera image to see that certain tweezers have atoms and certain tweezers have no atoms. And via then engineering your sort of frequency tones that you play, you simply sort out the tweezers with no atoms and throw them away, and you only keep the tweezers with atoms in them. And you sort of rearrange things until you have this sort of 1D kind of grid of atoms. And so you can see, for example, this is the picture that we can take before we've done any sorting. Some sites have 1 atom, some sites have no atoms. And so this is kind of the way we can see it. So basically, there's a particular amount of photon counts or amount of light that will hit our sort of camera. If there's no light, then there's no atom. But if there's a good amount of light, there's one atom. And then we'll sort of simply move out the empty trap and put in a filled trap there. And so you can see a little video of this sorting actually happening. So these are sort of sites that don't have atoms. And then we sort of sort them all so that there's a chain of always filled traps. And so, people can scale these up by simply sending in more powerful lasers and putting in more RF tones, frequency tones. And to actually give you a sense of what this looks like in the lab, it's very clean to talk about when it comes to concepts. But in actuality, things look very messy. You have many sort of cables and optics, and all these are sort of meant to essentially direct laser light around so as to project them into where the actual sort of science is happening, sort of in your vacuum chamber. Because at the end of the day, you're essentially attempting to capture single atoms. And so there's a lot of fine alignment and sort of overlap between light that must be made. Yeah, so how am I doing on time? I think.
Take your time. We got plenty
Okay,
of
so I
time.
will take my time then.
Yeah.
So the bits in qubits. So I talked about how we can sort of construct these things from single atoms, but I never actually told you, well, what's the 0 and what's the 1? So you may have heard, or remember from high school chemistry or like any later class you took, that there's this kind of like erroneous Bohr model for the atom, where simply you have these many orbits that correspond to different excited states. And so naively, you might say, okay, well, what if I just pick the 0 to be the ground state, and I pick the 1 to be the first excited state, and sort of the 0 will just be when the atom's sitting in the ground state, and then I can put an atom in the excited state by exciting it, to that state. And I have a 0 and a 1 that I can tune with a laser beam, essentially. Now, the problem with that is you may have also learned that the excited state is unstable, so the atom will very quickly decay out of it. So if you had, a qubit that was formed that way, you'd have kind of a crummy bit, and that, the 1 would not be a 1 for very long. So what we do instead is we actually rely on this thing called a hyperfine state, wherein the sort of coupling between the nucleus and the electron of an atom actually sort of imparts a special relativistic effect that actually pulls apart this ground state energy to form two hyperfine states that are effectively ground states and very stable, but split by a very precise energy splitting that for rubidium-87 we know to be, for example, 6.8 gigahertz. And those sort of hyperfine levels will correspond to our 0 and our 1. So that's kind of the bit. And now having a bit, we now need to think about how do we do gates. Now for sort of, the sort of NOT gate or sort of single bit operation, such as, flipping from a 1 to a 0, that's pretty straightforward actually. The way we do that is we simply, take a laser beam or some other source that will transfer the atom from 1 to 2, and we can just shine that onto the atom. If it's in sort of the 1 state and it gets hit with this kind of light that moves it up, then it'll simply kind of run up from the sort of 0 state to the 1 state. And if it's in the 1 state, then seeing this energy will actually de-excite it back down to the 0 state. So if we know our timings, we know our frequencies, we can kind of arbitrarily transfer the atom back and forth between the two levels. And so that's how you go. Essentially, you could do sort of a NOT gate, essentially, right? If I had a 0 and I wanted to apply a NOT gate to a 0, then it would come out as a 1. In this case, then I would start my atom 0, I hit it with this resonant light, it would flip up to the 1 state, and I have essentially flipped its state by applying my laser light. The 2-qubit gate now is a bit harder. So, classically, for sort of 2-qubit gates, you have these kind of like AND gates or OR gates that we talked about earlier. And now we need to think about how do we actually get two sort of qubits to interact with one another in sort of a controllable manner. And this is kind of a challenging thing that's actually figured out fairly recently. I'd say it kind of really took off in the 2010s. And this is using these things called Rydberg states, which are highly, highly excited energy states. For example, an excited state number of 50 that are very, very far away from the electron and have very huge energy scalings, and that they are just very far away from the nucleus and are very susceptible to sort of like external sort of fields and other types of interactions. And what you can do is essentially by sort of using actually 2 laser beams to transfer an atom to this n equals 50 excited state, you can realize sort of almost these controlled logic effects. And that you have this effect called the Rydberg blockade. Since these atoms are so large and so energetic, what happens is that if you place 2 atoms very close together in this thing called the blockade radius, wherein sort of the actual size of the atoms begins to maybe start to overlap a little bit, and you sort of attempt to excite both of them to the Rydberg state, that is actually forbidden in that the excitation of the first atom to the Rydberg state will impart a large energy shift on what the sort of resonance of the second atom is. And essentially, it'll block off the ability of the second atom to enter the Rydberg state. And sort of vice versa, if the other atom enters the Rydberg state, then it stops the first atom from going to the Rydberg state. And so with such a scheme and some additional engineering, you essentially realize these kind of controlled operations, wherein sort of if one atom is in this particular state that then can be transferred to the Rydberg state, then it'll prevent the atom, the other atom from entering such a state. And that's sort of how you realize these kind of Q-qubit operations. Then the sort of measurement process, the question of how do you actually read out kind of the state of the atom, is also kind of a unique thing in that sort of it's not particularly trivial just to kind of ask the atom or measure a voltage. In this case, what you have to do is essentially shine a light that will sort of couple a particular state to a transition that when it decays back down will then emit a photon that you can see or that your camera can see and collect. And what you're going to do is you will sort of place a light that will sort of transfer an atom in the one state to this excited imaging state. It'll sort of be transferred up by your light, and then it'll decay back down and emit a photon. And if it's in this one state, then this operation will occur successfully, right? In that you've specifically chosen your laser so that the frequency difference between the one state and this excited state is precisely correct. If the atom is in the 0 state, then that earlier frequency you picked is now wrong. It will no longer successfully transfer the atom up to the state that the imaging state that causes a photon emission event that can be collected on the camera. You now just see total darkness. So the thing that distinguishes these 2 states is kind of the darkness or the brightness that you sort of see after you apply this kind of imaging light. Whether photons appear and whether sort of that light couples correctly sort of each state to sort of the imaging excited state is what determines the brightness or darkness. Okay, so I think I have been talking for a while, so I might just discuss this problem and just kind of go to questions. So, I mean, this just sounds like a really complicated analog computer, right? I mean, people had these ideas of analog computation a very, very long time ago. Let's not use zeros and ones. Let's have a continuous infinite degree of freedom of like many like a very wide sort of variety of voltages. And so why did we not just do that? Well, the issue is errors are very hard to correct. So when you go to a continuous form of computing, wherein sort of the actual value of the voltage begins to matter, well, how do you fix, a voltage that was meant to be 0.55 and end up at 0.57 or 0.56 or 0.54? You essentially have an infinite amount of errors that can occur for any given sort of computational value. And so that's why we did sort of digital computing, right? It's a 0 or it's a 1. And then, as long as you cross a threshold, even if the voltage fluctuates a little bit, you'll still be above or below the threshold. And that's pretty easy. And also, to sort of correct classical computers, it's pretty straightforward. You simply, so say you have a 1, and you're worried that this 1, as you sort of pass it to your friend, there might be some funky operation that flips it to a 0 on accident, and that's, for example, an error that might occur. If you want to protect against that, you can simply clone your 1 3 times, and then, if you measure 1 1 0, then oh, okay, an error happened on this sort of operation. I see that 2 out of the 3 of my clone bits are both 1, and so I know I should have the right answer is 1. If 2 sort of bits get flipped in this process, then you can still tell that an error happened in that, I originally was sending a string that was supposed to be either 111 or 000. But now there's, I'm getting a string that has a 1 and a 0. So something must have gone wrong. This will tell you that an error occurred, but now we can't really fix it because there's no sort of voting mechanism to know, what's the majority, what's the correct kind of answer. And the really big problem is, well, if all three of these get flipped, then you have no clue what happened. You don't know if an error occurred or not. And that, both of these options look pretty perfect. And so I guess I'll conclude on just the fact that, well, the nice thing about quantum error correction, the sort of punchline for quantum error correction is that unlike analog computing, the errors are actually digital, but the computation is analog. So you kind of get to combine both of these two worlds, and the fact that you can actually fix errors with the fact that you actually have this, albeit kind of very challenging to engineer, phase that you can use for algorithms. And this is kind of the big takeaway. But before I say that this is all doable, I'd like to highlight some challenges. In quantum sort of theory, measurement is destructive. So as soon as you measure the thing you're doing computation on, you've destroyed it, and now you can't compute with it anymore. So any sort of logical or algorithm that requires you to check the state of something or try to understand if its state is the correct state so as to fix an error on, well, you can't do that because that destroys it as sort of a thing you want to compute with. And secondly, you can't simply do what we did in the classical case and just duplicate all your bits, because sort of quantum mechanics stipulates this no cloning theorem, that you can't actually sort of copy quantum information. And finally, I guess I address this, are errors analog as well? Since you have this continuous phase, no, errors are actually digital. And this comes from sort of a fact that quantum mechanics actually is sort of linear. Things sort of just add on top of each other, and actually errors can all be sort of broken down to 3 simple classes that you can use various algorithms to try and detect and correct. But yeah, this is kind of the general summary. And I guess I will sort of eschew the rest of these slides and simply say that, these sort of devices are sort of very challenging to build. And for us, actually kind of realizing the devices in this lab, it takes a team of very talented and hardworking individuals. So this is sort of our team that built kind of the mess of wires and optics you might have seen earlier. And this is sort of the principal investigator of the group, Dan Stanford-Kern. And yeah, skip the rest of the stuff and just do some questions. Yeah.
I'm curious, so you mentioned that when you actually read the qubit, it collapses to a 1 or a 0.
Mm-hmm.
So how do you store information in a retrievable form that's more meaningful than just like a 1 or a 0?
Yeah, so that's a good question. This is kind of one of the other challenges, what is, for example, memory when it comes to a quantum system? So the way you store, for example, phase information would be you would like to kind of essentially freeze the sort of quantum state of an atom. And so over time, because your atoms are coupling to the environment, the phase kind of gets smeared away by the environment, and that sort of the information you can think of as leaking into the environment. And if you have something, for example, like a rubidium-87 atom that we use, there's a particular time scale at which this information just leaks away and is totally gone. But there are other sort of systems or particles that have very long, what is called phase coherence. So the memory of their phase actually lasts for a very long time. So people talk about ways of attempting to essentially transfer the phase information from, for example, something you'd like to do computations on to then kind of particular things that are suited that have very long phase coherence that can actually sort of essentially freeze this phase information in time for a substantial period of time. And you need to sort of essentially transduce the atoms information into kind of this memories information. That could be one method, for example.
Yes, then do we need to kind of change our understanding of what a computer is, like when we're dealing with quantum computers? If it's is there actually ever going to be a quantum computer that has like a hard drive per se, or is it something totally different that we can't it's not going to be a one-to-one replication to the computers that we use today? If you can predict that.
That's a good question. I think, people are trying to essentially, realize, quantum memories and so on and so forth. And there are actually ways of like preserving quantum information for long periods of time, in particular in sort of like different systems as well. So you could, for example, realize sort of like a quantum memory like thing. That's definitely not sort of infeasible, thing like that. And I imagine, I mean, it'll be kind of somewhat similar to how we do classical computing, that you ask for essentially some algorithm that gives you an answer, and indeed you'll get that answer. And it's not the case that you want to sort of infinitely store the phase information in like your hard drive, for example. You might want to store some output on like a classical type system or something. And this phase information only lives for as long as you're doing the computation. You generally probably won't want to be holding the phase information forever. That is true, I would say.
All right, cool. Thanks.
Yes.
I'm also kind of curious. So you mentioned that, in order to understand what the measurement of the qubit is, you kind of have to do it a bunch of times. And so that, maybe you want to measure it 10 times or whatever. So generally, like, is there a good understanding of like how many of these atoms we need to make a solid measurement? Like, is 10 okay? Do we need 50 in order to understand what the phase measurement of a bunch of coherent qubits is? 1,000, a million,
Yeah. So the idea of a lot of these algorithms actually is that you use these kind of various probabilities and sort of interference between the phases to kind of say, for example, I'm doing let's say I'm doing like a database search. And let's say I have 10 items and I map each of these potential items onto a single qubit. And I'm saying I want to find the 9th qubit in a very quick way. So what I'm going to do actually is I'm going to run this algorithm, and the phases are going to evolve over time. And what's going to happen is the probability of measuring this qubit is going to increase and increase and increase as I run my algorithm. So my algorithm is actually created to maximally yield this result when I measure it. And past some probability, say like 99%, is when I say my algorithm is done and I stop. And then I measure this and I get my right result with like a 99.5% probability. So it is the case that you actually maybe don't need to do many repeated measurements, and that my algorithm is purposely designed to sort of maximally give my sort of right answer the highest probability, essentially. Yeah, question.
Is there a reason to use rubidium specifically, or do you?
Yeah, so the use of rubidium for this type of thing is kind of a historical reason and also a technical reason, that rubidium-87 is what is called like an alkaline atom, so it only has one valence electron, only one sort of outer shell electron. And what that implies, it has a very simple structure, meaning a lot is very well known about it, and it makes it very easy to laser cool. But that also gives it particular restrictions in that its simplicity, and it sort of disallows you from doing sort of particular neat kind of tricks to correct errors, for example. And that's why people have moved on to other things that are more complicated, like ytterbium, which sort of has a richer structure, has more outer shell valence electrons, making it sort of harder to work with in some circumstances, but also gives you more kind of tools to play with. So, there's kind of a very wide spectrum of sort of neutral atoms people will work with when it comes to this kind of neutral atom quantum computing. There's rubidium, there's strontium, there's ytterbium, and it's unclear, I guess, currently, at least what the best one is. And so, yeah, not a sort of particular choice, just it happens to work. Yeah.
Would it, for all the instruments that you mentioned, would it be easy to modify or adjust for the other atoms?
No, I would say it is essentially like impossible to modify a system that is supposed to work with rubidium to work with strontium or cesium, and that all of the transition frequencies are entirely different. And the lasers do not have the bandwidth to tune from, for instance, all the required rubidium excitation frequencies to the strontium or cesium or so on and so forth. So once you pick an atomic species, you're kind of stuck with it. And this presents like a particularly interesting case, and that you may have seen that there's many kind of quantum computing companies actually beginning to emerge. And so if a company actually chooses the wrong sort of atomic species to work with, and 10 years later we find out that like everybody who wanted to work with rubidium actually was kind of an idiot, and they should have been using ytterbium the whole time, these companies are kind of screwed in that they've invested tons and tons of money into laser systems and particular tricks with this particular atom. But then if somebody says, oh, ytterbium is the right thing to use, or strontium is the right thing to use, then it's not so straightforward to simply say, okay, let's just swap onto that and then have it done like the next day or something.
Got a question on Zoom.
Yeah.
This is from Joe. Is it time consuming to set up an experiment in quantum computing, and how long does a computation test last for each run?
Yeah, so I guess to give a sense of time scale, So the initial kind of apparatus required to actually accomplish all the steps to sort of trap single atoms in the optical tweezers, not talking about gates or anything, just the simple sort of capability to hold single atoms in tweezers and arbitrarily move them around, I would say took maybe 70 years to actually build up sort of all of these kind of different systems and whatnot. Then to realize the sort of lasers and operations required to excite atoms to the highly excited, for example, n=50 Rydberg states to do 2-qubit gates, that I would say took, will take, or is taking, took, or I'd say order of 2 years to 3 years. And this sort of, the single qubit gate excitation effort is a bit more straightforward. I'd say that is maybe like a 3-4 month time scale. But that's kind of the general gist of things. But it should be noted, I guess, that when it comes to like a laboratory setting, these things are typically built by like 4 or 5 people. Whereas, if there was like an industry company with kind of many people working on it, perhaps it could be much faster. But that's the time scale.
Very good.
Yeah.
When I look at these pictures, I think of, classical computers from 60 or 70 years ago. And I'm curious if there's, with classical computers, we want to measure, how many transistors fit on a microchip, and that's like a measure of our technological advancement with that. Is there an analogy with quantum computers? Like what do people use to measure the progress of the technology or the efficiency?
Yeah, so this is one thing I didn't really talk about. So for the case of quantum computing, it is not the case that sort of simply having more bits, like building like a huge array, sort of actually means you're doing better, and that we actually need to build these things called logical qubits, which consist of kind of many of these individual atoms and whatnot kind of tiled together in a particular way to form a very explicit kind of block that we use for error correction. And what you're looking at to know if a computer is doing better or not, first is sort of the error rate. So when you do any sort of operation, say for example, a 2-qubit or 1-qubit operation, a gate operation, what is the fidelity, what is the accuracy at which the sort of operation goes successfully? And when you are able to go past a certain threshold, then when you begin to increase sort of the amount of sort of atoms helping in your error correction, you begin to sort of suppress errors that sort of scales with sort of the sort of amount of atoms you're kind of incorporating in this error correction. So what people want to see, the benchmark at this point of how actually these computers are doing, is can you sort of build huge atom systems that consist of actually many logical qubits, not just individual atoms? And when you incorporate these logical qubits into cycles of quantum error correction, do you actually suppress error rates that scale with, this is the term is called the distance of the code, but you can think of it as kind of the amount of sort of helpers in your error correction routine. Does it actually kind of reduce the errors that build up in your system? Because you can think of like these errors as essentially doing random things during your computation that are modifying your end result. And so if you cannot realize a computer that gives you, the correct end result, then regardless of how many bits you have, if they all suck, then at the end of the day, it's kind of meaningless. But to build up sufficient logical qubits, you need many, many physical qubits. And to give a sense of scale, so for example, for something like Shor's algorithm, which people, is the biggest kind of, I guess, buzz algorithm you may have heard, and to break RSA encryption would require millions of sort of physical qubits. And the current record for neutral atoms, which I'm showing here, consists of, I'd say, 6,100 atoms. And at this scale already, the laser power required to generate the optical tweezers to trap the atoms is beginning to melt the microscope glass that is used to form these objectives. So there's a variety of engineering challenges, both in materials, but also in laser technology, that is required to actually hit the system scales required to do practical algorithms.
So much. These are both great talks. Yeah. So Science Bubble happens monthly, but usually we take December off. So we won't have a program in December, but plan to be back in January. Probably at the South Branch, but thank you so much.
Like intuition, the evolutionary process that led to breast cancer, something so yes.
And this is the QR code, if y'all would like to join.
Oh, yeah.
Animals on it.
Oh, I see.
Secrets.
Yeah, yeah.